Um, we need to welcome again into part 3 of chapter 3. So in this part, we will continue the rest of our slides. So I will go through example 3.4 one more time. In this example, we have a transfer function, and we need to find the differential equation which is associated with this transfer function. To do this, in fact, we need to do cross multiply. So we will just do cross multiply. And in this case, in one side, we will have s cubed plus 9s squared plus 26s plus 24 multiplied by c of s. And on the other side, we will have 24 multiplied by r of s. Apply inverse Laplace transform. So Laplace transform of s cubed multiplied by c of s, it will be 3 triple dot. 9s squared multiplied by c of s, it will be 9c double dot. 26s multiplied by c of s, it will be 26c dot. And finally, 24 times c of s, it will be 24c, equal 24r. So now we are converting it into time domain, and this one will be the differential equation. If you want to go back from this differential equation to the transfer function, you just need to apply Laplace transform one more time. From this one, we can assume a zero initial condition, and we can we're assuming zero initial conditions, and therefore we had this transfer function, which is c of s divided by r of s. So now if we need to find the static space representation of this equation, we need to assume, or we need to define states. So I will call the first state, it will be x1 equal c. Just differentiate this one more time, so it will be x1 dot equal c dot equal x2. So this one will be my first order differential equation. Differentiate equation 1, so you will get x2 dot equal c double dot, and I will call this one x3. This one will be my second first order differential equation. Now we will go to the third. Differentiate equation number 2 one more time, so we will have x3 dot equal 3 triple dot. And when you have 3 triple dot, it is equal that part. So we need to get that part in one side. So we will get it from this equation 3.56. So it will be minus 24c minus 26c dot minus 9c double dot plus 24r. So in fact, this is that part. I need to move that part to the other side with negative sign. So finally, just substitute those values, because we need to get state equation in the form of x dot equal ax plus pu. So in the other side, we need to have only x and u, x and inputs. So we will look into c. What is the value of c? We can see that the value of c from this one equal x1. So this one will be minus 24 x1 minus 26 multiplied by c dot. What is c dot? C dot is x2 minus 9 multiplied by c double dot. C double dot is x3 plus 24r. I will just call r as u, because this is my input. So now we have 3 first order differential equation. We need to write those 3 differential equations in a matrix rotation. So it will be like this one. I will write it here. So in one side, we will have here my states. First derivative, it will be x1 dot, x2 dot, x3 dot equal a matrix multiplied by a vector, which is ax, which is my state, x1, x2, x3, plus another vector multiplied by the input, which is u. We will look into equation 1, x1 dot equal x3. So coefficient of x1 will be 0, x2 will be 0, x3 it will be 1, this one will be 0. So this is the equation 1. We will go to equation 2. Equation 2, it will be x2 dot equal x3. Oh, sorry, x2. This one should be 1. This one should be 0. Equation number 2, x2 dot equal x3. So this one will be 0, this one will be 0, this one will be 1, also this one will be 0. We will go to equation number, so now we finished equation number 2. Now we will go to equation number 3. We will write the coefficient. Coefficient of x1 is minus 24. the coefficient of x2, it's minus 26. Coefficient of x3, it's minus 9. Plus 24 times u, so we will have here 24. So this is my state equation. This is my state equation. So, if you, there is something called the block diagram showing those phase variable nodes. In fact, if we need to do it, I can do it in a separate page. Or in fact, it's the most important is equation, my state equations. So I can write my equations here one more time. So we have x1 dot, in fact, it's equal x2. And we have here x2 dot equal x3. And we have x3 dot equal minus 24 x1 minus 26 x2 minus 9 x3 plus 24u. So those are the three equations. So you need to start by summing point. So we need to start, I will try to draw it here one more time. So we need to start by drawing a summing point, and the output from this summing point, it will be x3 dot, right? x3 dot. And just integrate x3 dot. When you integrate it, you will get x3. Right? And remember, x3 equal x2 dot. So in fact, x3 equal x2 dot. So when you integrate x2 dot, you should get x2. And from equation 1 here, x2 equal x1 dot. So in fact, x2 equal x1 dot. When you integrate this one, you will get x1. And finally, you will have y. Maybe y equal x1. It could be something else. So now we will go back to the summing point. We will look into equation number 3. What is the value of x3 dot? x3 dot, it's minus 24 x1. So I will get this one, multiply it by minus 24, and we will add it here to the summing point by plus. We will look into x2. So x2 will be coefficient minus 26, and also it will be like this one with plus. x3 is the same, but it will be multiplied by minus 9, and it will be an input here. So now we got x3 dot equal minus 24 x1, minus 26 x2, minus 9 x3, plus 24u. Remember this one, so this one will be plus. This one will be again 24, and the input to this one will be u of t or r of t, right? So it will be like this one. So with this, we call it block diagram of your system. In some problems, it's important to plot this block diagram showing your phase variable, So we call it phase variables. So in this example, we just solved it already. So we got the state equations, as you can see here. And after that, you want to write the output equation. This one, we call it state equation. And this is the most important part of representing dynamics of my system. Now we need to write the output equation. For the output, as I told you, you just need to select which state you want to measure. So if you want to measure x1, so y equal x1. So it will be like this one, 1, 0, 0, multiplied by my state vector, which is x1, x2, x3. So it will be like this one. If someone else, he want to measure x2, maybe someone, he said, no, I want to measure x2. So in this case, y equal x2, and it will be 0, 1, 0. As you can see, it's very easy to write the output equation because it's based on your requirements, which variable you want to measure, right? So imagine x1 is a displacement, x2 it is a speed, and x3 it is acceleration. So which parameter you want to measure, it's based on your selection. Okay, so now we need to convert a transfer function with polynomial in numerator. If you have in the numerator here a polynomial, how can we deal with it, right? It's easy. We just need to decompose it into state equation and output equation. So we'll just decompose it. We know it will be 1 divided by the denominator multiplied by the numerator. So we will divide it into 2 blocks, or multiplication of 2 blocks, right? So it will be like this one. So it will be 1 divided by that part first. The input will be r of s. The output will be states x of s. right? So the output from this one, it will be states. And after that, it will be x1 of s, because this is the lowest state, x1. It will be x1. We have also other internal states or internal variables. It will be x2 and x3. Why x3? Because this one third order. So we should have, in fact, we should have a state vector here called x1, x2, and x3. So when you decompose it into multiplication of two blocks, the output from the first block should be x1, right? And after that, we will have another block. The input to this block will be x1 of s, and the output will be c of s. And what is inside here, it will be this polynomial. So that is it. And getting the state equation, x1 of s divided by r of s, or getting x1, x2, x3, it's no problem. This is easy. And for the output, this is the output equation, right? So y of s will be c of s. It will be this polynomial multiplied by x of s. Just do multiplication. So it will be b2 x1 double dot. So if I want, I mean, it's here, it's written here. So I can say that if you apply time inverse Laplace transform, so we can say that y equal b2 x1 double dot, right? Plus b1 x1 dot plus b0 x1, correct? And after that, you need to find what is x1 dot. In fact, x1 dot, it's x2. So just replace this one with x2. And you have x1 double dot. x1 double dot, in fact, it will be x3. So y will be b2 multiplied by x3 plus b1 multiplied by x2 plus b0 multiplied by x1. If you want to write it in matrix notation, so it will be like this one. So y will be this vector multiplied by x1, x2, x3. What is the coefficient of x1? Coefficient of x1 is b0. Coefficient of x2 is b1. Coefficient of x3 it's b2. So it will be like this one. And we can call this one is the output equation. Okay, so maybe we need to okay, we have an example here, example 3.5. This problem differs from 3.4. So the numerator has a polynomial in S instead of just a constant term. I mean, it's a function with, yeah, this function. Yeah. So it's example 3.5. We need to convert a transfer function with a polynomial in numerator. So we will start with this one. Compose it into two blocks, right? The output from the first block will be x1 of S. And of course, we will have some internal variables, x2 of s, x3 of s. So the input will be r of s. So it will be 1 divided by this denominator. And we will have here numerator. So this block, the input will be x1 of s, and the output will be c of s. And just apply. I mean, we can do it here. You can just apply inverse Laplace transform for the first part and the second part. And try to get state space representation. We can start, in fact, with this one. We will have x1 equal that part, or we can say that x1 of s divided by r of s equal 1 divided by s cubed plus 9s squared plus 26s plus 24. Do cross multiply and apply inverse Laplace transform. So it will be x1 triple dot plus 9 x1 double dot plus 26 x1 dot plus 24 x1 equal r, right? So just try to find some states. So we can say that okay, my states will be x1 will be x1, right? Differentiate x1 dot equal x1 dot equal x2. x2 dot differentiate, it will be x1 double dot equal x3. And finally, we will have, okay, I cannot write here, so it will be x3 dot equal x1 triple dot equal, from this equation, it would be minus 24 x1. What is x1? x1 is x1, is my state. Minus 26 x1 dot, what is x1 dot? Is x2. Minus 9 x double dot. What is x1 double dot? It's x3. Right? Plus r. So this is my state equation. So we have now here equation 1 equation 2, this is equation 3. In fact, from those three equations, you can just write your state equation. So it will be x1 dot, x2 dot, x3 dot equal matrix A multiplied by state vector x1, x2, x3 plus p multiplied by the input u. So we will look into equation 1, x1 dot equal x2, x1 dot equal x2. So this one will be 0, 1, 0. This one will be 0. For the second equation, x2 dot equal x3, so it will be 0, 0, 1. This one will be 0. For the last equation, x3 dot equal minus 24, x1 minus 26, x2 minus 9, x3 plus u. So this is my state equation. Let us now try to get the output equation. So the output equation, we call it y of s or something. I will just call it y of s equal this part, numerator, s squared plus 7s plus 2 multiplied by x1 of s. Apply inverse Laplace transform. So we can say that y equal x1 double dot plus 7 x1 dot plus 2x1. Write it in a state equation. So it will be 2x1 because x1 is a state plus 7 x1 dot. What is x1 dot? x1 dot is x2 from equation 1 plus x1 double dot from equation 2 here, it's x3. So plus x3. Write it in matrix notation. So we will have a vector multiplied by state vector, which is x1, x2, x3. So the coefficient here, it will be 2, 7, 1. So we can say that this is my output equation. So now we can write the output equation of your system. So now we have state equation, we have output equation. So this is here just explanation. How can we do this in details? You can see it in the book. So just to try to read those, those steps. Finally, you will get this one. And also from the output equation, you would replace states, those x1 dot with x2, x1 double dot with x3, so you can get the output equation. So we did that here. So we have input, we have state equation and the output equation. Okay. In this example here, transfer function, decompose transfer function. So it's just if you want to plot the block diagram of your system. As I told you, if you want to plot this one, you just need to get your state equation, and from state equation and the output equation, will be the output equation, right? So if you can go to output equation, what was the output equation? 1 equal x1, x2, x3. Can go back to it to see the output equation. So it would be 271, right? It was 271, 2, 7, 271, right? So 2x1. So now we have here 2 multiplied by x1. You will get this one plus 7 multiplied by x2. This one is 7 multiplied by x2 plus 1 multiplied by x3. This one is 1 multiplied by x3. And of course, for the state equation, we go to the state equation, we go to the x3 dot. So x3 dot was, if we can go back to the equation, what was x3 here? From this equation number 3, x3 dot equal minus 24x1, minus 24x1, minus 24x1, minus 26x2, minus 9x3 plus r, right? So this is a third equation, if you can remember it. So just you need to plot it here. You need to draw it here. So I will do it here one more time. To plot this graph, you need to start from the summing point. So I will start from the summing point. The output from the summing point will be x3 dot. Just integrate it to get x3. Integrate it to get x2. Integrate it to get x1. So now we are done. Now try to reconstruct x3 dot. So x3 dot is minus 9 x3 minus 9 x3. So this one will be multiplied by 9. This one will be negative minus 9 x3 minus 26 x2. It will be like this one, 26 minus 9, 26 times x2 minus 24x1. So it will be something like this one, minus 24. Plus r, so it will be like 1 multiplied by input r. So it will be that part. Once you have x1, x2, x3, you want to reconstruct the output equation. So the output equation is easy because from this equation it's 1 times, so it will be 1 times x1 and 7 multiplied by x2, this one plus, and x3 multiplied by 1. So this one will be y of t. So it's very easy to plot the block diagram of your system, and it will help you to understand things. So now we have skill assessment exercise, and in this skill assessment exercise, you have a transfer function, and from this transfer function, we need to find the state equation, right? I would like to solve this one with you. So, okay, it is not okay. I need to solve this one with you. So we need to decompose it, right? So it's similar to the last example. So to solve this example, I will give you a hint. So so this one is second order system. So we have x1 and x2. So we will start with one block. And this block we will have 1 divided by s squared plus 7s plus 9. It's second order system. So the input to this system will be maybe r of, yes, it's r of s. And we will get the output. It will be x1 of s, right? And we will have the second block, which is 2s plus 1. We will have the output here, which is c of s or y of s, right? So we will decompose it as we did in the last example. We will use the first part here to write the state equation, and the second part will be used for getting the output equation, right? So, so the first part, in fact, there is an approach, in fact, for getting it without even solving. So as you can see here, we can say that, okay, x dot equal, the first row here, it will be 0, 1. The second row will be the coefficient starting from here, multiplied by negative. So it will be minus 9, minus 7, minus 9, minus 7, plus 0 divided by 1. I mean, I don't want to make you confused, but this is quick approach. There is quick approach for writing your state equation. And for the output equation also, it will be the coefficient from here to here, coefficient 1, 2. You see, coefficient here 1, 2. So it will be 1, 2. But for this one, it will be minus, we will start by minus 9, minus 7, minus 9, minus 7. So, so I will let you to solve this one. And after solving it, we found that this is system matrix A, this is B, this is C, and we have also B equals 0, right? So we will get matrix A, B, C, A, B, this one, plus x dot equal AX plus BU, Y equal CX plus DU. So we can say that, okay, now system matrix is 0, 1, minus 9, minus 7, right? And B equal this matrix. C equal 1, 2. Just remember this one, it's row, this one is column, and the D equals 0, right? So those are the matrices which are describing our state space representation. So now we need to use Python or MATLAB to simulate the response of the system, right? So how to convert state space representation into transfer function? How to convert from state space representation to transfer function? So if your system is given in the form of a state space, how can we get transfer function from a state space representation? In fact, we will start from a state space representation, which is in time domain. As you can see here, it's x dot equal ax plus bu, y equals cx plus bu. Just apply Laplace transform here. Laplace transform of x dot, it will be sx of s. This one, it's constant multiplied by x, so it will be a multiplied by x of s plus bu multiplied b multiplied by u of s. For the output equation, it would be y of s equal cx of s plus du of s. We need to get from this equation, we need to get x of s. because this is my states. So from this equation, we will write it like this one. It will be S x of S minus AX of S equal BU of S. So we just try to move AX of S to the other side with negative sign. Take X of S as a common factor. What will be remaining here? It will be SI minus A. Why I? Because we are subtracting a matrix. I mean, when we are matrices, I cannot say that this one it's S minus A because S is scalar, but I is unity matrix. So we need to say that it's SI minus A, where I is a unity matrix, identity matrix. I is an identity matrix. So if A, for example, is 2 times 2, I should be this one. Is 1001. It will be like this one. So now we will get X of S. So if you want to get X of S, you need to divide both sides by SI minus A, or subtract both sides by the inverse of SI minus A. So when you multiply both sides by SI minus A to the power of -1, so in this case, we can get X of S in one side, right? So it will be X of S would be SI minus A inverse multiplied by U of S. Now you got X of S. So we will substitute this value into Y, right? Because now I need to get my transfer function, and my transfer function should be the output divided by input, right? My transfer function, G of S, it should be the output, Y of S, divided by the input. So now we will go to the equation. This equation one more time. We will go to this equation, and we will just substitute the value of X of S, which we got here, because we need to remove X of S from the equation. So we will substitute X of S with this value. So in this case, Y of S will be C multiplied by X of S. What is X of S? It's that part. So it will be C multiplied by SI minus A inverse BU of S plus DU of S. Now you can see that we have U of S as a common factor. Take it as a common factor. So what will be remaining is C multiplied by SI minus A inverse multiplied by B plus D. So this part. Now we need to get the transfer function. Transfer function will be Y of S divided by U of S. So we will divide both sides by U of S. So we will get Y of S divided by U of S. So when we divide both sides by U of S, this one will disappear from the side, and what will be remaining is C multiplied by SI minus E inverse B plus D. So this one will be my transfer function. So the idea here, if you have your system represented in a state space representation, and you have A, you have this A matrix, you have B, you have C, you have D. You will get this formula, and if this substituting A, B, C, and D into this formula, you should be able to get your transfer function. So just a direct substitution, you will be able to get your transfer function. So now we need to take an example. So it's example 3.6. So you have a system which is 3 times 3, an A matrix, it's a 3 times 3. We need to find the transfer function, which is T of S equal Y of S divided by U of S. We have this is my state equation. This is my output equation. So first, we need to get SI minus A, and after that we will get its inverse, right? So S multiplied by identity matrix, it will be this one, right? S multiplied by I. Just as identity matrix here is 1 0 0 0 1 0 0 0 1 multiplied by S. So just multiply H. So S times 1, it will be S. S times 0, it will be zeros. 0 S 0 0 0 S. So this one will be SI minus A. This is my A matrix, right? Subtract each element by element. So it will be S minus 0, it will be S. 0 minus 1, it will be minus 1. 0 minus 0, it will be 0. 0 minus 0, it will be 0. S minus 0, it will be S. 0 minus 1, it will be -1. Here it will be 0 minus minus 1, it will be +1. 0 minus minus 2, it will be +2. And finally, we will have S minus minus 3, it will be S plus 3. Now we need to get the inverse of this matrix. The inverse of this matrix, in fact, it is the adjoint of this matrix divided by the determinant. First, I will try to get the determinant of this matrix. If you want to get the determinant of this matrix, so in fact, you need to select one row or one column, and it's better to select row or column which has many zeros. But in our case, if you select this one or this one, it doesn't matter because both has only 1 0 here. So I have here 1 0 and I have here 1 0. So just select anyone which you like. So you need to cross this one and cross this one and find the determinant of the square matrix inside. So it will be S multiplied by S plus 3 minus 2. So it will be plus 2. So in fact, this one, it will be multiplied by S, right? Plus negative plus. Negative 1, it will be plus 1. Cover this one like this one. So it will be 0 times this one minus 1. So it will be plus 1. We will get here 1. Just make it simple. So inside here, it will be S squared plus 3S plus. Inside here, it will be S squared plus 3S plus 2 multiplied by S plus 1. So in fact, it will be S cubed plus 3S squared plus 2S plus 1. So this one will be determinant of your matrix. Now we need to get the adjoint of the matrix. In fact, the adjoint of the matrix also, it should be also done in the same way. So the adjoint of the matrix is, so we will start with this S. Start with this S. Cross this row, cross this column, get the determinant of the square matrix here. It will be S times S plus 3 minus 2. So it will be S squared plus 3S minus 2. It will be plus 2. So it will be this amount. We will cross the second. We will get the determinant of the left. So it will be 0 multiplied by this one. It will be 0 minus 1. It will be plus 1, in fact. But minus, it will be plus 1. But in fact, I need to do it in more steps because we use here the sign plus negative plus something like this one. So we will get, I guess I need to do it here. So I need to clean first. So I need to maybe clean, right? So I can show you how to get this, yeah. So first I need to get the adjoint of this matrix. So okay, we will make it, the adjoint will be like this one. Oh, sorry. So the adjoint will be, yes. So it will be a matrix like this one. I need to get the adjoint for S. If you want to get this one, you need to cross this row and this column. Get the determinant of this matrix. So it will be S times S squared plus 3S minus 2. It will be plus 2. That part. We will go to the next element, which is here. But just remember, we add and we multiply by something sign, which is plus, negative, plus, negative, plus. Here also it will be plus, negative. Here it will be negative, plus. Just remember that you are multiplying by those. And we will take transpose afterwards. Okay, so we will go to the second element here, which is minus 1. So we'll take the determinant of the rest. It will be 0 multiplied by this one. It will be 0 minus 1. It will be plus 1. Plus 1, but in this location, we need to multiply by negative. So it will be negative 1. We will go to the third element here. It will be 0 times 2, which is 0 minus S. It will be minus S, right? We will go to the second row. We will go to this 0. We will cross this line, We will take the determinant of the rest. It will be minus 1 multiplied by S plus 3 minus 0. So it will be minus times minus, it will be plus S plus 3. Yes, like this one. The element in the middle here, cross. So it will be S times S times S. It will be S squared plus 3S. It will be, okay, the one in the middle, So it will be, yes, it will be S multiplied by S plus 3, correct? It will be S times S plus 3. We will go to this element here. You need to clean it. Clean. So just remember signs plus negative plus negative plus plus negative. We have here negative plus. So now we go to -1. So if you need to get it for -1, so we need to cross this line and this line. So it will be S times 2. It will be 2S plus. It will be 2S plus 1. 2S plus 1 multiplied by negative. So it will be minus. So S plus 1. We will go to the third row, which is that part here. So it will be plus minus plus, so it will be -1. I need to clean because I cannot see it. Yes. Okay, so it will be -1 -1. It will be +1, just a +1. This one will be 1. We will go to the next element, which is 2 cross row and the column. So it will be -s. -s multiplied by negative, so it will be +s. Finally, we will go to S plus 3, so it will be S square minus plus. So it will be S square, just S square. It will be S square. And we need to take the transpose of this one. Remember to take the transpose. So after getting those numbers, we need to take the transpose. When we take the transpose, just to convert each row into a column or vice versa. So I'll start my first row. This row, I will write it as a column. So we will start by writing S squared plus 3S plus 2. -1 minus S, so we will write it as a column. We will go to the next row. It will be S3. We will write it as a column. It will be S3 S times S plus 3 minus 2S plus 1. So we will write it as a column. And finally, we will have 1S squared. So this is the adjoint of the function. It takes time for getting it, but once you try to practice it, and of course, if we have an exam, we get 2 by 2. We will not get 3 by 3 because 3 by 3 is difficult. So now we got Si minus E inverse. This is SA minus I inverse. You have also B, which is 10, 0, 0. You have C, you have D, right? So just substitute those values into the formula in order to get the transfer function, right? To remind you, it will be, I need to go back. So we need to substitute into this form to get my transfer function, right? It will be C multiplied by the inverse B plus D. So it will be C, my transfer function, it will be C multiplied by Si minus A inverse B plus D. This one will be my transfer function. So just, you can see here, we will be happy, in fact, because you have B many zeros, in fact. So if you have this function, and if you try to multiply it by C and B, right? So I need to do it in I will just put B here. So imagine that this is Si minus A inverse. We need to multiply it by B from right side and by C from the other side. So I will write B here, which is 10, 0, 0, correct? And from that side, I need to write C, which is 1, 0, 0, correct? So when you multiply this row by this column, I mean, this one will be 0, this one will be 0. So we'll have only 10 multiplied by that part, correct? So the result of this multiplication, it will be only this column, but multiplied by 10. Remember, just this first column multiplied by 10, right? And after that, we will multiply this column by a row, which is 1, 0, 0. So what will remain? In fact, it will be 10 times S squared, right? So this multiplication, it will be like this one. It will be 1, 0, 0 multiplied by 10 times S squared something. The second row will be -10. The third it will be -10s, right? There is no space to write it here. So after that, we will multiply this row by this column. So what will remain will be only that part, 10 multiplied by s squared plus 3s plus 2 divided by that part, which is s cubed plus 3s squared plus 2s plus 1. So now we can get our transfer function from state space representation. So the idea here, if you have your system represented in time domain, it could be a differential equation. If it is a differential equation, apply Laplace transform. From it, you will be able to get your transfer function. If your system is in state space representation, it should also be possible to use this formula for getting your transfer function. So both are very important. So now we have here a quiz. It's a system, and we need to get the transfer function, right? So and it's much simpler, right? Because it's 2 times 2. Just we need to get the transfer function. So just remember, transfer function is C multiplied by SI minus A inverse B plus D. You have A, you have B, you have, in fact, D equals 0. So this one is A, this is A matrix. So for this A matrix, we need to get first SI minus A. So just as a hint, SI minus A, it will be like S0, 0S, negative, this A matrix. So it will be minus 4, 4, minus 1.50, right? You will get this one, and after that, you will get the inverse. If we need to get the inverse, which is SI minus A inverse, so to be the adjoint divided by the determinant. First, I need to write this one. So this one, it will be S plus 4, S plus 4. And we have here the state divided by 2, right? Positive. We have here minus 4. We have here 0 minus, or S minus 0, it will be S. Now we need to get the inverse of this one. So if you need to get this inverse, we need to divide by determinant of this matrix, which will be S multiplied by S plus 4, minus 4 multiplied by 3 divided by 4, so it will be S multiplied by S plus 4, minus, it will be plus 4 multiplied by 3 by 2, so it will be 6, right? So it will be 6. As you can see here, we got the same number here. So it will be S squared plus 4S plus 6. So what is missing now is to get the inverse, which is adjoint, and to substitute into the equation of the transfer function to get the part. So I will leave it for you to do. So now we need to do a simulation. We did that before for a system represented in, if a system is given in transfer function, we solve for y of t and we plot it in Python, for example. So now we need to simulate our system if it is given in a state space representation. So you have this example here. You need to go to the link and test it with it. So first, I just need to define the matrix A, and I need to define my column vector B, C, and D. So this is the most important, right? And we know that x dot, this is a state space representation, which is x dot equal ax plus bu, and y equal cx plus du. It's a general form, right? So if you want to simulate it in time domain, you just need to write it like this one: x dot equal a multiplied by x in this line. X dot equal, I'm just writing it here in Python. So x dot will be dot product of a and x plus b times u. Once you calculated x dot, you need to integrate x dot to get x, because this is x dot, not x. X dot means its rate of change. It is a first derivative. So first I need to get x dot, and from x dot you need to get x. So x will be x plus this x dot, right? We'll call it x dot. Multiplied by delta t, small time step. This is a time step which we are using for integration. So after getting x dot, you just need to update the value of x. So x will be x plus x equal x plus x dot multiplied by delta t. Delta t, it's a very small time step. After calculating x, you need to calculate the output, which is y. So just apply the equation y equals cx plus du. So we have this line here, which is y equal c multiplied by x dot product of c and x plus dot product of d and u. If you have x, multiply x by c, you will be able to get y. This system, it's just open loop. So to simulate it, in fact, I just try to write it put it in closed loop. So if you want to put your system in closed loop, the system will be like this one. This is my system, right? And I will connect a controller here with K, for example. This is my system, G of S. We will have a summing point. The input here will be R of T. This one will be negative feedback of the output. So I just need to apply a controller to my system. So first I need to calculate the error signal. So error signal will be R minus Y, right? I need to calculate error signal here. So to close the loop, you need to calculate error. So error will be R minus Y. After that, you will send this error signal to your controller. This one is your controller. You can start with B controller or BI controller, for example. In this example here, I selected BI controller. And the BI controller, in fact, U equal KP multiplied by error plus KI multiplied by integration of error. This is the equation of BI controller. It's very simple. So if you want to simulate it, you can just say that, okay, differentiate both sides, or you can just directly write U equal KB multiplied by error plus KI multiplied by integration of error. I call it sum of E, integration of error. And I need to write one more line here to integrate error. So sum of E will be sum of E plus E. I'm just store Y and R for reference, and I changed the reference here. In fact, I'm starting with here R equal 1, and the when time is greater than 5,000, I will change R from 1 into 2, and the when time is greater than, or time steps is greater than 10,000, I will change it back to 0.5. So the reference will be like this one. It will be 1, and from 1 it will change to 2, and from 2 it will be like go back again to 0.5. So it's like driving your car, for example, and you are driving at 50 kilo per hour now, and you will go to maybe 70, and you will go back again to maybe 30 kilo zone, for example, right? Like this one. It could happen, right? So I try to check the response of my system. And when we run the system, I need to select values for KB and KI. When you select value for KB and KI, you will be able to achieve a response which you want. So the response of my system will be like this. So I can simulate the response of my, in fact, this example, it's full control system. Your system is given in time domain. So we have status-based representation, and you have status-based representation, and also we designed a controller, which is BI controller. We closed the loop, and as you can see, the code is very, very simple. So just need to go to the previous link and try to play with this one. So it's BI control for a system in status space. Just press on this link and I try to make some changes to it. And in this system, we use this system here. We use this A matrix, B matrix, C, right? And of course, D equals 0. So this is A, this is B, this is C, and this is D. I mean, if you are working with MATLAB, they have a function called the status-based representation. So, you just represent your system in a status base, and after that you can get the transfer function from it. So all our calculations, in fact, we can avoid it if we can use any software package from MATLAB or from Python. So, but we don't want to do this, in fact, because we need to learn how things are done. So, so at the end, linearization, we have been talking about linearization in the end of chapter 2. So at the end of chapter 3 also, there is a small part about linearization, but it's one advantage of using a status-based representation over transfer function is its ability to represent systems with nonlinearities. In fact, when we are working with a status-based representation, we don't need to linearize a system. But if you want to work with transfer function, you must linearize it, because transfer function is designed for linear time invariant system and single input, single output. We don't have those restrictions in the status-based representation. The ability to represent a nonlinear system does not imply the ability to solve the zero-state equation. We can use Taylor series, which is a representation of a function as an infinite sum of terms that are calculated from the values of the function derivatives at a single point. So if you have a function like exponential x, you can use Taylor series to expansion. It's called Taylor series expansion to try to linearize it. So we can write e of x as a summation of some terms. It could be 1 plus x squared divided by a factorial of 2 plus. So there is formula for each function. And usually when you try to linearize, we can just use maybe the first two terms, only that part, if you want to linearize it, for example, or the first 3 terms. So it's a quantitative estimate, quantitative estimates on the error introduced by the use of such an approximation. So we can just use Taylor series expansion for linearizing some elements in our system, but we will not go into it, and we will try to make things simple. At the end of this chapter, in fact, you don't need to submit this chapter report, but if you would like to answer those questions, try to go to a small set of questions in the problem section and try to solve those problems. And if you have questions, you can just contact with me. And if you would like to submit your answer to Canvas, just let me know so we can open the system so I can get it from you and try to give you feedback. So this is the end of chapter 3. I hope that you will be able to understand it very well. And if you have any questions, we can discuss it again. So thank you very much.